In today's video, we're going to be talking about the first derivative test, which is a way we can figure out what a graph looks like using its first derivative. You may remember in past lessons, if we had a derivative, say f of x is equal to x squared, we could take the first derivative, which of course is just f prime of x, and that's equal to 2x by the power rule. Using this first derivative, we can actually find out some things about the graph without having to actually graph the function. So let's talk about that here. But before we go too much further, I want to talk about the monotone function theorem, also known as MFT. That sounds a lot like NFT, but unlike that, MFT is actually useful. If f prime of c is greater than 0, then the function f is increasing at that point. If f prime of c is less than 0, it's decreasing. And if it equals 0, then the function is not changing, aka the slope is constant. C is simply just the point on the graph that we chose for this function. I also need to mention that if f prime of c is equal to 0, then that point is not an extremum, aka it's not a maximum or a minimum, which we'll talk about more in just a second here. So what this theorem tells us is that we can use the first derivative of a function to figure out where a graph is increasing and decreasing without having to draw the graph at all. Let's say we had something that looked like this. Say this is 0, this is 8, and this is -7. Let's say our graph looks something like this. This red line represents the first derivative of our function. Wherever the function dips below the x-axis, this function is decreasing, or negative. Wherever it is above the x-axis, this function is increasing, or positive. We can use this in order to determine where functions are increasing and decreasing. The points of interest, such as -7, 0, and 8, are our critical points, which I talked about in my last video. We'll talk more about that when we do an example problem, as it's a little easier to understand there. Let's do two example problems for this video. In our first example, we have the function x cubed minus 3x squared minus 9x plus 1. We have two things that we're trying to find. We need to find where f is increasing and decreasing, and we also need to find the extremums, aka the maximum and minimums of the function. Since this is a huge pain in the butt to graph, we should use the first derivative test to find all of this information. So what we're going to do is build a sign chart. Remember earlier when I was talking about 0, 8, and -7, and we figure out where it's increasing and decreasing? This is a sign chart. We're going to find something that looks very similar to this. Obviously, this isn't the one we're going to use, but we'll find that as we solve this problem. The first thing we need to do in this problem is find the derivative of f of x. That, of course, is f prime of x, and we're only looking for the first derivative here. We'll talk about the second derivative test in a future video, but let's do the first derivative test first. F prime of x is just equal to the derivative of f of x. Using the power rule, we get that the derivative of x cubed is 3x squared. The derivative of -3x squared is -6x. And the derivative of -9x is just -9. The derivative of 1 is just 0 because the derivative of any constant is just 0. Now we need to find the critical points using this derivative. To find those critical points, we just need to find where this equals 0. Because if it equals 0, then that is either a relative maximum or minimum because the function is changing from increasing to decreasing. So this function turns into 3 times x squared minus 2x minus 3 is equal to 0. And I gotta say, this function looks awfully factorable, and in fact it is. So we can change this function once again. We still have our 3 at the front, but since we have an x squared, we know that one of our factors has to be x and the other one also has to be x. And this of course still equals 0. Now we just need to find two factors that add up to be -2 and multiply to be -3. And those two factors are -3 and +1. X times x is x squared, x times 1 is x, -3 times x is -3x, x minus 3x is equal to -2x, and then -3 times 1 is -3. So this factor does work. Now that we have this, we know that each one of these individual factors must equal 0. We don't have to worry about the constant, but we do need to worry about these two, because if one of these two equals 0, then the whole function equals 0. 3 minus 3 will equal 0, and -1 plus 1 will equal 0. So x is equal to 3 and -1. And these are our critical points. And we'll need these when we build our sign chart, which we're going to do next. Let's build out that sign chart. Our sign chart will look something like this. I'm gonna mark -1 here, 3 will be way over here, and I'm gonna mark 0. I know that's not even, but for our purposes, it's fine. So at -1 and 3, we know that our function will equal 0. So we need to find points in order to figure out where x is increasing and where it's decreasing. So let's find points that are not -1 and not 3. For example, let's plug in f prime of 2. In other words, we're going to plug in 2 for every f prime of x. But since this is equal to f prime of x, we're going to use this because it's a little easier to understand. It'll make more sense in just a second here, but since these two are equal, we're going to use the more factored version. So f prime of 2 is equal to 3 times 2 minus 3 times 2 plus 1. Here we have a positive number, here we have a positive number, but here we have a negative number, which means this entire function is negative. Let's try f prime of 0. It's not one of our critical points, and I already marked it on the graph, so may as well try it. F prime of 0 is equal to -9. Now the reason I know it's equal to -9 is because since this function and this function are the same, if we were to plug in f prime of 0 into our original function, these two would cancel out and we just get -9. Of course, this is a negative value. Now let's plug in a number that's slightly higher than 3, say f prime of 4. This is equal to 3 times 4 minus 3 times 4 plus 1. And since all of these are positive, this part of the function will also be positive. Oh, and actually I made a mistake just a minute here. We're trying to plug in f of -2 here, so this would be -2 minus 3 and -2 plus 1. Since these two are both negative and this is positive, this part of the function is actually positive. Sorry, I made a little mistake there, but this actually does make a huge difference and also corrects what I thought was right. Anyway, sorry about that. Let's continue knowing that this is now positive, this is negative, and this is positive. So behind -1, the function is increasing. So we know it looks something like this. It's going upward whenever we go lower than -1. But whenever we reach f prime of 0, which is slightly higher than -1, the function is decreasing. So it goes below the x-axis as such, something like that. But then we also know when f prime reaches 4, it's positive again. So that means the function continues to increase after f prime of 3. So now that we know this, we know that this area here is increasing. We know that this area between -1 and 3 is always decreasing, and we know all the area behind -1 is increasing. I should probably make that a little clearer, so this will be positive, negative, and positive. It's a little hard to see with the red on red. So what this graph tells us is that we know where f is increasing and decreasing. Remember, by the first derivative test, wherever f prime of x is less than 0, f is decreasing, and whenever f prime of x is greater than 0, f is increasing. So for part A, f is increasing. I'm going to write INC for increasing at, and we're going to use interval notation to mark where it's increasing. We know that anything below -1, it's increasing. So from -infinity all the way to -1, the function is increasing. And this function is still increasing at -1 and begins to decrease after -1. So we can include -1 here by denoting that with a bracket. Then f continues increasing after x equals 3. So we're going to put a little u here. This u stands for union. At 3, the function is still decreasing, so we can't include it. But from 3 to infinity, the function is increasing. Now, where's the function decreasing? Let's write that over here. And decreasing, which will be denoted with DEC dot. And the only place where this function is decreasing is between -1 and 3, as denoted on our sign graph. So it's decreasing between -1 and 3. So that's all of part A. Now we need to find the relative maximum and minimum. So what are our relative maximums and minimums? Well, -1 is a relative maximum, and 3 is a relative minimum. But why is it a relative maximum at -1? Well, remember, our function is increasing all the way up until -1. At -1, the function starts to decrease. And whenever the function is increasing and then starts to decrease, we have a relative maximum. And then at x equals 3, the function's been decreasing up until it reaches -3. Therefore, it dips like this, goes from decreasing to increasing. And when it does that, the function is a relative minimum. Think of the bottom of the parabola and the top of a parabola. So here's our answer. F is increasing at -infinity to -1 union 3 to infinity, and decreasing at -1 to 3. By the way, this is a parenthesis, not a bracket. And the relative maximum is at -1, and the relative minimum is at x equals 3. Let's do one more example for this video. In this example, we have the function f of x is equal to x squared plus 8x minus 3. And we want to find the same things as last time. We want to figure out where the function is increasing and decreasing, and we want to find the maximums and minimums of this function. Once again, if we find the first derivative, we can figure out all this information. So let's find out the first derivative of x squared plus 8x minus 3. This is denoted as f prime of x, and the derivative of x squared is equal to 2x using the power rule. The derivative of 8x is equal to just 8, and the derivative of any constant is just 0, so we don't even need to write it. So this is our derivative, and we can use this to find all of our information. Once again, we need to find critical points and figure out where this function equals 0. So in order to do that, we can subtract 8 from both sides. This turns into 2x is equal to -8, and if we divide both sides by 2, we get that x equals -4. And this is our only critical point in this problem, unlike last time where we had 2. So our sign chart is actually super easy to draw. Since we only have one critical point, we just have to put -4 here. And also, since we only have one critical point, we only need to test one number on the negative side and one number on the positive side of -4. So let's do that. First, let's plug in f prime of -5 and figure out if it's increasing or decreasing. This is equal to 2 times -5 plus 8, which is equal to -2, and obviously that's negative. Now we just need to plug in one number that's greater than -4. For this example, we'll use f prime of -3. It's just slightly above it, just like how -5 is slightly below it. This is equal to 2 times -3 plus 8, which is equal to positive 2, which is positive. So on the left-hand side of negative 4, or on the negative side, this function is decreasing, but on the right side, or the positive side, this function is increasing. So our sign chart is simply going to look like this. A little easier to draw because we just have to draw a line like that. So on this side, the function is decreasing or is negative, and on the right side, the other side, this function is positive or increasing. So using this sign chart and the data we found, we can figure out the absolute maximum and minimums of this function, along with where it's increasing and decreasing. First of all, at negative 4, since our function is equal to 0, this function is neither increasing or decreasing, so it cannot be put into our interval. In other words, we're just going to be using parentheses and not brackets. To answer part A, f is increasing, denoted as INC because I'm lazy and don't want to write increasing, at negative infinity, oh, that's an 8, negative infinity up till 4. But we cannot include 4 because at 4, this function is equal to 0, which is neither increasing or decreasing. And this function, f, is decreasing at 4, or sorry, negative 4, I meant to write that there, to infinity. Once again, we can't use brackets because we cannot include negative 4, and we also cannot include infinity with brackets since infinity isn't really a number, it's just a concept. So this is part A answered. For B, what are the relative maximums and minimums? So we know that negative 4 is a minimum for f. There is no maximum on this function. The critical points, aka the only one that we have, is either a minimum or a maximum. And since we only have one critical point and it's a minimum, we don't even have a maximum in this problem in the first place. So this is our answer. And to be safe, I would write relative minimum, but since we do know this is a parabola, you could write absolute minimum and probably get away with it. The second derivative test gives us additional information about the graph that the first derivative test didn't give us. In the first derivative test, we could figure out where a function is increasing and decreasing, we could find critical points, but we couldn't find inflection points or concave up and downness, which we'll talk about in this video. First of all, some quick review. Let's say we had an f of x such as x squared. The first derivative, f prime of x, would equal 2x by the power rule. The second derivative, or f double prime of x, would then just be 2. Essentially, you just take the derivative again. It's just another step. And we're going to use the second derivative to find out more information about the graph, and using information from the first derivative test along with information from the second derivative test, we'll be able to graph our functions. So let's talk about some of the stuff that I was talking about just a second ago. So I've written two rules down about the second derivative test. If f double prime of x is positive on the interval from a to b, then the graph is concave up on that interval. And if f double prime of x is negative on a to b, then the graph is concave down on a to b. Now you may be wondering, what do I mean by concave up and down? Well, let's draw a graph to make this a little easier to understand. Here's our xy plane, and we'll use blue to draw the graph, because why not? I haven't used it much in a while. Let's say we have a graph that looks something like this. I don't have a numerical function to go along with this, but it'll show us what I'm talking about. Here's one way to remember it. If this little curve could hold water, then it's concave up. If the water spills out on either side, then the curve is concave down, like on this side. Another important thing to know is what I've written down over here. If f double prime of x is greater than 0, then f prime is increasing. In other words, the graph is increasing at that point. If f double prime of x is less than 0, then f prime is decreasing. And I want to highlight this point roughly there. This point is an inflection point. The inflection point on a graph is when the graph changes concavity from either concave down to concave up or concave up to concave down. These points will be very important when we graph these functions because we need to know where the concavity changes. We'll talk more about the inflection point when we get to graphing. We're not there just yet. So let's talk about the second derivative test itself. The second derivative test states that c is a critical point. And if f prime of c, aka you plug in c to your function, is less than 0, c is a relative maximum. So it's the top of a curve, kind of like this little graph here. If f double prime of c is less than 0, c is a relative minimum, aka the bottom of a curve. Kind of like this, kind of like just x squared. And if f double prime of c equals 0, the test fails. And we're about to start graphing, so in this top right corner, I decided to draw a little diagram that can help you visualize everything better. If your graph looks something like this, it's concave up, it could hold water, but the function is also increasing. Similarly, this function is also increasing, but is concave down. It would spill water. Here, the function is concave up, but it's decreasing. The function's getting smaller and smaller as we move to the right. And same thing over here. This function is concave down because it would not hold water, and it's also decreasing. This will come in handy when we start graphing in just a second here. So like I was saying, we're going to use the same example we used last time, which was x cubed minus 3x squared minus 9x plus 1. And we're going to use this function in order to find where the function is concave up, concave down. Remember, refer to this graph if you get stuck. we're going to figure out the inflection points marked as IP, and then we're going to actually graph this function, because using the second derivative test and combining that with the first derivative test, we can actually graph the function and get it pretty correct. So first of all, we should probably find both of these derivatives. F prime of x, which we found last time in last video, is equal to 3x squared minus 6x minus 9. The derivative of a constant is equal to 0, so we don't have to write that. But we also need f double prime of x, aka the second derivative. So what's the derivative of this function? Well, we just do the derivative again. This is equal to 6x minus 6. And then once again, a constant just turns into 0 when you take its derivative. So this is our second derivative. And in order to find the inflection points, we need to make this equal to 0. Just like in the first derivative test, we need to set the first derivative to 0 to find the critical points. By the way, the critical points of this function, which are right up here, labeled as CR, are equal to -1 and 3. So first, let's add 6 to both sides, like so. So 6x is now equal to 6. Divide by 6 on both sides, and we get that x equals 1. This is our inflection points right here. Now, just like in the first derivative test, we're going to build out a sign chart. And, well, we only have one point that we need to check, so we're just going to mark 1 right here. What we're going to do is we're going to plug in numbers that are less than 1 to figure out what's going on the left side, or left of our inflection point, and then plug in a number bigger than 1 to figure out what's going on the right side of our point. And since we only have 1 point, we only need to check one number on this side and one number on that side. Nice and easy. So first, let's try f double prime of 0 equal to, which would then be equal to x just being 0, 6 times 0 minus 6, which of course equals -6. This number is negative, therefore this side is negative over here. F double prime of, let's just choose a number higher than 1, say 2, is equal to 6 times 2 minus 6, which is equal to 6. That's a positive number, therefore on this side we are positive. And you know what? I'm going to make those signs a little bit clearer. We're going to put a red plus sign here and a red negative sign here. There we go. I hope that's a little easier to see. So with just this sign chart, we can actually answer part A. Where is this function concave up and concave down? Well, wherever the function is negative, the problem is concave down. So we're going to answer A over here. It's probably going to get blocked while I'm teaching, but I'm going to write it over here. This function is concave down from -infinity. Remember, we don't include infinity because it's not really a number, to -1. And we don't include -1 either because at -1 we have an inflection point. So we can't actually include it as concave up or concave down. This function is concave up at 1 to infinity. And once again, we cannot include either one of those. So that's part A answered. Let's move on to part B. What are the inflection points? Well, we already know our inflection point just based on our sign chart. So B, the inflection point, is equal to 1. We only have 1 in this function. So that's nice and easy. Now part C is going to be the hardest part. We're going to use all this room over here to graph. So I'm going to write C over here, and we're going to graph this function out. Let's draw a little XY plane in order to do the graphing. And you know what? Let's use green. I haven't used green much recently. That should be a good color for this graphing. So we're going to mark the important points. First of all, we have our critical points at -1 and 3. So here on the graph, I'm going to mark -1. We're going to mark 3 over here. And the other point that we're interested in is +1 because that's an inflection point. So here's +1. So now that we've marked all of our points of interest, let's talk about some of the values that we already know. First of all, from the first derivative test, we know where this function is increasing and decreasing. So I'm going to write all the relevant information here. Increasing. So this function is increasing from -infinity to -1. Union, that's what that is union. So we have a gap in between here, but we have two different areas where it's increasing. So we union them or put them together. And then this function is increasing from 3 to infinity, right there. This function is decreasing. By the way, decreasing is labeled DECR and increasing is labeled INCR. This function is only decreasing from one area, from 1 to 3. This function is concave up or CU. I don't know if I mentioned that, but concave up is CU. It's just a shorter label. This function is concave up from 1 to infinity, aka forever after point 1, and then concave down from -infinity all the way up to 1, because that's where our inflection point is. So then it flips to concave up after that. And something else we know based on our critical points, which I labeled up here and on the graph, is that at the critical points, there is a relative maximum and a relative minimum. So what we're going to do is we can plug in -1 and 3 to figure out exactly what point is our relative maximum and what point is our relative minimum. I'll save you the trouble. At -1, y is equal to 6. And at 3, this function is equal to -26. So this is not to scale. because I do not want to draw this to scale because it would not fit on my board. So basically, if you wanted to figure out these points for yourself, you could just plug in whatever these critical points are to your original function f of x, and that would give you your relative maximums and minimums. And remember, we know that this is a relative maximum and this is a relative minimum because we know at the top of a concave down curve is a relative maximum, and at the bottom of a concave up curve is a relative minimum. So we have all the information we need. First of all, we are decreasing down here, and then it goes up and up and up and up and up, and it hits negative 1, 6. And we know that this is a relative maximum. So then the function starts to decrease from here, and at 1 is the inflection point. So it starts to go down. I just went directly through the number 1, but I'll redraw it. And then it reaches this relative minimum here at 3, negative 26. And then at 3, it continues to go upward. So our function looks something like that. And this is a pretty good rough estimate considering we don't have calculators to use for these problems. And, well, we're just doing it by hand. And using just the second derivative test combined with the first derivative test, we can graph just about any function. So just to review, part A, we wanted to find where the function is concave up and down. We know that this function is concave down from negative infinity to negative 1, as you can see here, and that it is concave up from 1 to infinity, as you can see here. We know the inflection point is 1 because at 1 is when this concavity flips from concave down to concave up. And based on the first derivative test, we know our critical points were negative 1 and 3. And knowing where our critical points are helps us figure out what our relative maximums and minimums are just by plugging it into the original function. So, and C is just the graph. That's all we had to answer here. There's no other numbers here, don't worry. I hope you enjoyed this video. I hope it was helpful, and I hope you learned something today. If you'd like more Calculus 1 lessons, be sure to check out the playlist linked here, and consider subscribing. I'm uploading all of Calculus 1 to this channel along with Cal 2, 3, and other lessons to come in the future. I'll see you guys in the next video.